All right, so now we're going to talk about what is a crucial theorem when it comes to the theory of integration, and indeed much of what you'll do in calculus in the future. So what do we need to do here to get to this? Right? We need something called an area function. So here we're going to say f is continuous on the interval from a to b. And what we want to do is define this area function. So we define the area function as, right, what I want to do is I want to integrate my function f starting at a, starting at the left endpoint, and I want to integrate up to some arbitrary point x, right? So I want to integrate like this. Call this f of t. Okay? So, right, so what we're doing here is we're basically saying, okay, let's say we have some function here. Let's put a over here, b over here, okay? And then what I'm sort of doing is saying, all right, well, this area here at x, right, we move up here, and the area function tells me the area of this, right? And then as I move x around, that area, as I move closer to b, that area gets bigger. So here's a little demonstration of that in Mathematica. It is capturing the wrong window. One moment. Let me switch back real quick. We should be capturing this one. Okay. So we're looking here at this integral, right? Or sorry, at this definition here. All right, so again, a of x is this sum, right? And let's look at, a little visualization. When x is a, there's basically no area there, right? Well, it is 0. But as we let x get bigger, we can see that the area for a of x, just grows here. Okay? So this is what I want to think of as my area function, right? Again, it's just something that starts from the left side. Starts from the left side here. It's capturing my mouse in a position different from where it is. Right, so from the left side here, it's going all the way to this right side, right? And as I increase the value of x, you can see that it grows. All right, so back to the tablet here. So now that I have this function, what I actually want to do is I want to differentiate it, oddly enough. I want to say, well, how is this area changing, right? So, in order to differentiate it, we have to, set up that difference quotient. So, what I want to think of here is, let's look at, right. Actually, let me pull up Mathematica again here. So I want to look at things like this. Right, so I have this right here. So here's area of x plus h. Here's area of x. And the difference between them is this little spot v here. Okay? So let's think about this now. Right, let's see here. So I want to construct, right, a prime of x, I want to think about that. So this is limit as x as h approaches 0 of a of x plus h minus a of x over h. So again, let's go back here to Mathematica real quick. So a of x plus h is the area between these two green lines here. A of x is this area here where it leaves off this little gap. And then I've called v here the remaining area. Now, when h is pretty close to 0, this is a really tiny strip here. Okay? So because of that, we can actually think of this difference here. So v is going to be the difference. It's going to be a of x plus h minus a of x. So that difference, v, that's approximately just a little rectangle here, right? There's no big deal here. I'm just calling that a rectangle. H is going to 0 anyway. So what we can do is say that, well, this is the limit as h goes to 0 of, well, what is the approximate area there? Well, it's going to be h times f of x over h. Right? Let's look at this area here. Right? So the width of this strip right here is h, and the height of it, well, we may as well use the left endpoint to approximate the height. And again, once h gets really small, this doesn't matter anyway. Okay? So, well, when we're computing this limit here, these h's, of course, are going to cancel. And then this is now saying that the limit as h goes to 0 of f of x. But there's no h here anymore, so this is just f of x. So what have we done? What have we, managed to say here? Well, what we've managed to say is that, so a prime of x, by the way, this is also written as d dx integral from a to x of f of t dt. All this is just f of x. So all that happened when we differentiate this expression right here is this got popped in there. That was it. So this is saying that when we take the derivative of the definite integral of f, we just get the original f back. So the derivative does undo this integral, provided that we have this variable in the bound here, right? And this right here is what's known as the fundamental theorem of calculus. So the fundamental theorem of calculus. Right? Sometimes this is called part 1. Right? So here we have f is continuous on the interval from a to b. Then the theorem says that d dx of the integral from a to x of f of t dt, this is equal to just f of x. Right? So that's the first part of the fundamental theorem of calculus. This is, theoretically, it's the most interesting part of the fundamental theorem of calculus. Right? It says that derivatives and integrals undo each other. Practically, however, this isn't the most important part. Right? The most important part is what we're going to talk about now. So, let's think about what consequences we really have from this fundamental theorem of calculus. Right? It says that if I differentiate the area function, I get f back. Right? So what that means then, so this implies that the area function is actually an antiderivative of f. Right? So area function is an antiderivative of little f of x. Okay? So at least on the interval from a to b, right? We should add on a to b here, right? Because it's not defined outside of that. All right. So since that's true, we could say the general antiderivative is, right, we usually call this capital F of x. We could say, all right, well, this is a of x plus c, right? So what I'm going to do here is evaluate at endpoints. So we get f of a is a of little a plus c, and f of b is a of little b plus c. Okay. Now I'm going to do something interesting, and I'm going to subtract these two equations. Right? So f of b minus f of a, right? This is going to be a of b plus c minus a of a plus c. All right? So let's think about what happens here. Well, these cancel, and we are left with a of b minus a of a. And I want you to think carefully about why this is true. So, go back to some properties of the integral that we talked about. This is just a of b. Okay? So this gives us something really important here. Okay? What is a of b? Remember what the area function is. The area function is the integral from a to x, f of t dt. Okay? So this is a very, very important consequence from us. It actually gives us, the second part of the fundamental theorem of calculus. The fundamental theorem of calculus, part 2. Okay. So again here, we say f is continuous on a to b, and capital F is any antiderivative of little f on the interval from a to b. Okay, so it doesn't have to be, everywhere. Often it will be, but it just needs to be any antiderivative. Okay, then what these two things being equal mean is that a of b is the integral from a to b of, here I can actually write x, there's no harm, right? So then this has to equal f of b minus f of a. Right? And that right there is arguably one of the most important facts you can learn in calculus. Right? So let me just close this off with saying we have a notation that we often use for this right here. For expressions like this, f of b minus f of a, we will often write f of x, and then here we're going to write a vertical line, which means evaluated from a to b. Right? So get familiar with that notation. You'll see it quite a bit in the coming weeks. But yeah, hopefully you enjoyed this rather more theoretical video. Not much in the way of computation here. But again, I want to make the big connection here one more time that this fundamental theorem of calculus says, amazingly, that if we want to find this net change, this net area under a curve, all we have to do is pick any antiderivative, plug in the two endpoints, and subtract them. Right? And that gives us that net change, or that net area under the curve. Right? And, in my opinion, that is just an absolutely remarkable fact that we should be able to get a theorem like this. Right? See you next time.